Our topic of discussion is iron-carbon phase diagram. Iron-carbon phase diagram is significantly important because it forms the basis of the steel industry. Seen here is what may appear as section of iron-carbon phase diagram because the highest carbon weight percent you see on the horizontal composition axis is 6.7. In all steels and cast irons, highest carbon content is 6.7 weight percent. When the carbon content is 6.7% by weight, all the carbon is present as cementite or iron carbide. According to new convention, therefore, 6.7 weight percent carbon is replaced by 100 weight percent iron carbide, and what used to be iron-carbon phase diagram is now referred to as iron-iron carbide phase diagram. Let us now take a look at the different phases that you will likely come across in iron-iron carbide phase diagram. Iron-iron carbide phase diagram contains following solid phases: alpha ferrite, gamma austenite, cementite iron carbide, and delta ferrite. First phase we consider is the alpha ferrite phase. The alpha ferrite phase region, circled in red in the phase diagram, is a very tiny region that occurs in the lower portion along the temperature axis in extreme left of the phase diagram. Alpha ferrite phase is an interstitial solid solution of carbon in the body-centered cubic iron crystal lattice. As indicated by the iron-iron carbide phase diagram, carbon is only slightly soluble in alpha ferrite, reaching a maximum solid solubility value of 0.02% at 723 degrees C. Another very prominent phase in the iron-iron carbide phase diagram is the austenite phase, also referred to as the gamma phase. The area in this phase diagram, circled in red, is the single-phase austenite or the gamma region. Austenite is an interstitial solid solution of carbon in gamma iron with FCC structure. Austenite has much higher carbon solid solubility than alpha ferrite. The solid solubility of carbon in austenite is 2.08 weight percent at 1148 degrees C, that decreases to 0.8 weight percent at 723 degrees C. Next solid phase we talk about is the cementite or the iron carbide. In the iron-iron carbide phase diagram, cementite occurs in the extreme right adjacent to the temperature axis. Area circled in blue is where you will come across the cementite phase. Cementite is a hard and brittle compound. The next phase we consider is the delta phase. Like the alpha ferrite phase, delta phase also has a BCC structure. The interstitial solid solution of carbon in delta iron is called delta ferrite. It has a BCC crystal structure like alpha ferrite but with a larger lattice constant. Maximum solid solubility of carbon in delta ferrite is 0.09% at 1465 degrees C. And like the alpha ferrite phase, single-phase delta ferrite occurs along region adjacent to the temperature axis in the extreme left. The area circled in red at the top of the temperature axis in the left is you will come across the single-phase delta ferrite region in the iron-iron carbide phase diagram. We now consider different invariant reactions related to iron-iron carbide phase diagram. An invariant reaction for a binary alloy is one that occurs when three phases are in equilibrium. The first invariant reaction we consider is the paratectic reaction, represented by chemical equation 1 seen in this slide. Paratectic reaction occurs at 1495 degrees C, wherein liquid phase containing 0.53% carbon combines with delta phase with 0.009% carbon, leading to the formation of austenite phase with 0.17% carbon. The location on the phase diagram where paratectic reaction is likely to occur is marked with red circle. This slide highlights eutectic reaction. Eutectic reaction occurs at eutectic temperature. In case of iron-iron carbide phase diagram, eutectic temperature is 1147 degrees C and the eutectic composition is the liquid containing 4.3% carbon. As per the chemical equations seen here, liquid with eutectic composition when cooled below 1147 degrees C result in alternate fine structures of gamma austenite containing 2.08% C and the intermetallic compound iron carbide or cementite. The location on the phase diagram where eutectic reaction is likely to occur is marked with red circle. This microstructure of the material following the eutectic reaction can be seen in Figure 3. due to its appearance that resemble mother-of-pearl when observed under an optical microscope at low magnification. The eutectic microstructure is also referred to as pearlite. The other important invariant reaction that is of importance as far as iron-iron carbide phase diagram is concerned is the Eutectoid reaction. As per the chemical equation 3 seen here, during Eutectoid reaction, austenite phase containing 0.8% carbon at 727 degrees C dissociates into two solid phases, alpha ferrite and cementite or iron carbide. The red circle on the phase diagram in figure 1 marks the region where Eutectoid reaction occurs. We will now follow the microstructural changes that occur when iron-carbon alloys with three different compositions are cooled through eutectoid temperatures, 727 degrees C. We do that by first considering iron-carbon alloy with eutectoid composition containing 0.73% carbon. Please pay attention to the vertical dotted line in figure 2 to understand the microstructural changes that take place when the alloy with eutectoid composition is lowered in temperature from point A, on the dotted line, to point B. Point A on the dotted line is in the single-phase gamma region. So at point A, you will only see grain consisting of gamma phase. On the dotted vertical line when you traverse from A to B, the alpha phase will transform into alternating layers of lamellae of the two phases alpha and iron carbide. This microstructure that is formed as seen in figure 3 is called pearlite because it has the appearance of mother-of-pearl when viewed under the microscope at low magnifications. We now consider composition of the iron-carbon alloy to the left of the eutectoid, containing between 0.022 and 0.76% carbon. This is termed a Hypotectoid alloy. Please pay attention to the vertical dotted line in figure 4 to understand the microstructural changes that take place when the alloy with Hypotectoid composition is lowered in temperature as we move from point C to point F on the vertical dotted line. At point C on the dotted line, microstructure will predominantly comprise of austenitic phase. As we go down the dotted vertical line to point D in the two-phase region containing alpha and gamma, along with austenite phase, there is also emergence of alpha phase. As we further traverse on the vertical dotted line from point D to point E, the alpha phase, as seen in the schematic, grows in size. So at point E, just above the eutectoid temperature, along with the gamma phase, there is sizable amount of ferrite. When we cross the eutectoid and move to F on the dotted vertical line, the alpha phase continues to show its presence and the austenite transforms into pearlite with alternate lamellae of alpha and austenite phase. Therefore, at point F, the microstructure will consist of pearlite and the alpha phase. This alpha phase seen at point F is termed proeutectoid ferrite. Analogous transformations in microstructures result for hyper-eutectoid alloys, those containing between 0.76 and 2.14% carbon, when cooled within the gamma phase field is shown in the figure 6. Please pay attention to the dotted vertical line in figure 6. At point G only the gamma phase will be present. Upon cooling to point H, cementite phase will begin to form along the initial gamma grain boundaries. This cementite is called proeutectoid cementite, which forms before the eutectoid reaction. As the temperature is lowered through the eutectoid to point I, all the remaining austenite gamma phase is converted into pearlite, thus the resulting microstructure consists of pearlite and proeutectoid cementite.